To prove that a sequence converges, we wouldn't want to resort to the definition every time. So we'd like to have some tools or theorems on which we can rely on in proving that sequences converge to some limit, and such a tool is the limit arithmetic theorem. Now, when we look at it, it looks quite natural. So the limit of the sum, so if we have two sequences an and bn, and the sequence an approaches the limit a, and bn approaches b, then it is quite natural to assume that an and bn would converge to the sum. And the reasoning behind the proof is the following one. So since an converges to the limit a, then it will be as close to the limit as we please, provided that we go far enough. Similarly, with the sequence bn, it will be as close as we please to the limit b, and therefore, going far enough, the sequence, which is the sum of the sequences, will approach to the limit, which is the sum of the limits. Similarly with the difference and with product, but here it's a bit harder to prove. And finally, with the quotient, we need to be careful here. First of all, but the conditions here are quite natural. First of all, we need that the sequence is non-zero for every element, and this requirement is very natural because we want the sequence of the quotient to be defined. I mean, after all, we do not want, we cannot divide by 0, right? So in order for this sequence to be defined, we must have that bn is non-zero for every n. And secondly, if we want this to hold, that the limit of the quotient will be quotient of the limits, then of course we cannot divide by b if b is 0. So assuming those two conditions, that the sequence is non-zero and converges to a limit which is non-zero, and yeah, that convergence, bn converges to this non-zero limit and the sequence is non-zero, then the limit of the quotient is quotient of the limits. So now we'll see in Desmos a bit about the intuition of how this works and how we're going to construct the proof. Let us now explain intuitively of how the proof is going to work. Here we see two sequences, the blue sequence, which converges to its limit, and the orange sequence. Now, since both sequences are convergent to their limits, then for every epsilon, the sequence will be as close to the limit, as we please. This means that if I draw this epsilon stripe that we see here, right, then for every epsilon, the stripe can be as narrow as we please. Starting from some point, all the elements of the sequence will be within this stripe for every positive number. And the idea is, if we fix epsilon for the sequence of the sums, then we, for example, can demand that from some place, the distance of all the elements from the limit for this sequence will be smaller than epsilon half. Similarly for this sequence. So for this sequence, we can also take this stripe of width epsilon half, right? And so what we see here is that this blue sequence converges to the limit much faster than the orange one, right? And so we want all this, both of the sequences to be within the distance of half epsilon from the limit simultaneously, right? When we prove it. For this one and for this one, but they converge at different rates. So therefore, what we can do here is the following thing. So if we were to draw the n of epsilon for the first sequence, we see that for this n of epsilon for the first sequence, all the elements starting from this n of epsilon with index bigger than this n of epsilon, they will be in this epsilon stripe, or to epsilon stripe. Yeah, here we take actually epsilon half. So within this, so for every element with index bigger than this n of epsilon here, all the elements of this sequence, their distance from the limit will be smaller than epsilon half. However, it doesn't hold for this sequence. For this sequence, it converges a bit more slowly, but for this sequence, we have another n of epsilon. So say this is n1 of epsilon and n2 of epsilon. Now, what happens is that when we choose the maximal of those, then after this point, we see that both sequences are within this epsilon stripe from their limit, right? And therefore, if we demand that the width here, the distance here is epsilon half, and here is epsilon half, then the difference of the sums from the limits would be smaller than epsilon. That's the intuition. Basically, this sequence is as close as we please to the limit, and this one is as close as we please to its limit. So adding the elements of the sequence is basically the same as adding the limits, because the error would be as small. So now that we've seen the intuition in Desmos, let's give a rigorous proof of this theorem. Okay, so every proof starts with let epsilon be greater than 0, and this epsilon is going to be for the sequence of the sum. For the sequence an plus bn, we need to show that an plus bn, and bn minus a plus b, which is the limit, can be smaller than any given epsilon. Okay, so we start with a positive epsilon. Now here we're going to use the definition of the limit. That's the only thing that we can use. So since the sequence an converges to a and bn converges to b, then an can be as close as we please to a, and bn can be as close as we please to b. So restating this, this statement formally, and noting that epsilon here is reserved, we can say the following. We'll just use another later. We have that for every positive number eta, any positive number, it doesn't matter what's the name of the number, right? There exists n1 of eta and n2 of eta, such that for every n that is greater than n1 of eta, an minus the limit is smaller than eta. It's the same definition, right? It's every positive eta. And for every n that is greater than n2 of eta, because the sequences may converge at different rates, bn minus b is going to be smaller than eta. Now, here I'm being very formal. But later we're not going to be as formal, but it's still rigorous enough, provided that this step that we're doing here is understood. This is what can be done in principle. Now, since this holds for every eta, in particular, I can choose eta to be epsilon half, right? Every positive number. So given this epsilon, I can make this to be smaller than any eta, so I can take eta to be epsilon half. And then there will be number n1 of this eta, which is epsilon half, which is some n1 of epsilon. It depends, it's a function of epsilon. And similarly here, I can make this to be smaller than epsilon half. So choosing eta to be epsilon half and choosing n of epsilon to be the maximum of those two, so that both of those inequalities hold simultaneously for epsilon half, what we have is that for every n that is greater than this n of epsilon, so since n is greater than n of epsilon, it's greater than n1, therefore this inequality holds. And since n is greater than n of epsilon, it's also greater than n2 of epsilon, so this inequality holds. Now, using the triangle inequality for the limit, we have that for every epsilon, we have showed the existence of a number, natural number n of epsilon, such that for every n that is greater than n of epsilon, we have that the sequence, which is the sequence of the sum, its difference from the supposed limit of what I proved to be the limit, is by triangle inequality no more than this. But then, since this n is greater than n of epsilon, then this is going to be smaller than epsilon half, and this is going to be smaller than n half. Therefore, all this difference is smaller than epsilon, and it can be done for every epsilon. For every epsilon, we have demonstrated how to find this n of epsilon, and therefore the limit of an plus bn is a plus b, as desired. So we've proved this. Now, for the difference part, it's an exercise. It's exactly the same. So, and it's going to be exactly the same expression. So it's going to be here an minus bn, and here it's going to be a minus b, and it will revert exactly to the same expression and just the same argument. So do this exercise. It's a simple one. Okay. So for the third part, again, let epsilon be greater than 0. And first we consider the expression. We start working with this. So basically we want to show that an times bn would converge to a times b, provided that an converges to a and bn converges to b. Okay. So we need to show that for every epsilon, we can find such a place, such that for every n greater than n of epsilon, this can be made to be smaller than this fixed epsilon. Okay. So, and when we see this expression, I mean, this is where we should start, but how should we proceed? And now again, we show a very common and useful trick. We need to add and subtract a term which will going to mediate between this and this one. So the idea is the following one. We subtract this an minus b. b is the limit of this sequence, and add the same term. So we changed nothing here, but now we have something in between. So here we can take an outside, and we're going to have bn minus b, which we know we can make small. And here, what we're going to take outside is the absolute value of b, and then we are going to have inside an minus a, and therefore an minus a, we can make it as small as we please. So now this is all bounded by this expression. This is just equality. This is just triangle inequality, and then taking an outside from this part, and then taking b outside from this part. Okay. So now we're going to proceed with the same idea. So here we can make an minus a smaller than epsilon half, and we would like to make it divided by the absolute value of b. Now, it's going to be a bit trickier because I don't want to consider separately the case where b may be 0. Now, clearly, if b is 0, then it's simpler. This term doesn't exist, but I want to treat all cases simultaneously, so we'll see what we're going to do about this. And now, what about this term? So I want to say that bn minus b would be smaller than epsilon half, but I cannot divide by this varying term an. And what happens when n gets bigger? Maybe for some elements this just becomes very large. So here we use the theorem that we proved previously, that every convergent sequence, since we know that an is a convergent sequence, it converges to a, then it is a bounded sequence. So we know that there exists some positive number, m. So since the sequence is convergent, there exists some positive number, and I would say strictly positive, because I would want to divide by this m. And so if m, so it's non-negative, of course, but if m happens, even if we can choose it to be 0, we can choose it to be 1, or whatever. If it was 0, something that bigger than 0 also works. So with that loss of generality, m is positive and strictly bigger than 0. It's non-zero, right? And this m is an upper bound for the absolute value of the sequence. Okay, so now, again, looking at this expression, it is bounded by this m times this, times bn minus b, and plus this. And now, the same trick that we did for this sequence with the eta, now we will say that it is obvious that we can do it, right? So for this fixed epsilon that we have, since an converges to a, there exists n1 which depends only on epsilon, such that an minus a can be made smaller than any positive number that we please. Now this b is a constant value, so this n1 essentially depends only on epsilon. And this can be made as smaller than any positive number. So this is epsilon divided by the absolute value of b plus 1, and twice. This is a positive number. And so if I go far enough by the definition of limit, I can make this expression smaller than this. Now why this plus 1 here? Just to make sure that if b happens to be 0, that I do not divide by 0. We will see how it works for us. So here, basically, when I'm going to replace this expression by its upper bound, I'm going to have b over b, absolute value of b over the absolute value of b plus 1. So it's something that is strictly smaller than 1. We'll see how it works out. Okay, so we have this. And similarly, since bn converges to b, then there exists a number n2 of epsilon such that bn minus b can be made to be smaller than epsilon divided by 2m. And again, I assume that m is strictly bigger than 0, then it's not a problem to divide by m here. So this, for every n greater than n2, we have this inequality. And now, choosing n of epsilon to be the maximal of those two, we have that for every n greater than n of epsilon, we would have that this expression, which is bounded by this. And now I take bn minus b and I replace it by something that is bigger. So bn minus b is smaller than epsilon over 2m. So this term is bounded by this. And now I replace an minus a by something that is bigger than this, which is this. And so this term is replaced by this. And overall, this m reduces. So we have epsilon half. And here, epsilon half, this epsilon half that we have here, this is epsilon over 2. And here is this expression. Now, all I care about is that this expression is smaller than 1. And so all in all, this is even smaller than epsilon half. This is epsilon half. So all of it is going to be smaller than epsilon. So we have showed that for every epsilon, right, there exists this n of epsilon such that for every n that is greater than n of epsilon, the difference of an bn minus ab is going to be smaller than epsilon. Okay. So finally, now we're going to prove the result for the quotient. Okay. So to prove the result for quotient, we will show first that bn converges that if bn converges to b and the sequence is non-zero, and for every n and the limit is non-zero, then the sequence 1 over bn is equals to 1 over b. Now, why does it prove the result that we had for the quotient for an divided by bn? Well, because if we have the sequence an times the sequence 1 over bn, and an converges to a, and 1 over bn converges to 1 over b, then by the result that we have proved for this product, then this sequence an times 1 over bn is going to converge to the product, which is a times 1 over b, but we'll see it shortly. So, okay, so consider the sequence cn, which is 1 over bn. So since this sequence bn is defined, is non-zero, then cn is defined, right, for every n. The expression 1 over bn, since bn is non-zero, is defined for every n. And so is the quotient. The quotient 1 over b, since we assumed that b is non-zero, it is defined. So now we want to show that this approaches this. So again, we need to consider this difference. And so making a common denominator and doing some manipulations here, what we're having is that this is bounded by this, okay? And now what we want to show, here's a tricky part. We want to show that this sequence, basically we would want to say that this is, we would want to make bn minus b smaller than the absolute value of b times epsilon and times what? So what happens if this bn becomes very small? Then it's suddenly hard to bound, right? But we would want to show that this bn can be bounded from below by a number that is strictly bigger than 0, because bn converges, after all, to a non-zero limit. So since bn converges to b, there exists a number n1, such that for every n that is greater than n1 of epsilon, we can make bn minus b smaller than b half. And why the absolute value of b half? Why did I choose this? Well, because we don't know how small b is. And so the bound that we want to make is this bound that has to relate to b. And what we have here is that this is the other part of the triangle inequality. So just considering this part and this part, what we have is that this must be between this difference between the absolute value of b half and greater than minus b half. Therefore, the important part for us, that there exists some number n1, it's a constant, right? Such that for every n that is greater than n1, this bn is bounded below by this strictly positive number, because remember, we assumed that b is non-zero. So bn is, at least for n that is greater than n1, is bounded below by this, which is strictly bigger than 0. And therefore, this cannot, when bn is too small, then it can suddenly blow up to infinity. So at least for n that is greater than n1, this does not explode. Okay, so we can control this term and bound it by some constant. All right. So let us proceed. What about n that is not greater than n1? Well, then what we will consider is this finite set of absolute values. So we consider b1 absolute value up to bn1 absolute value. So this is a finite set, and this is a trick that we're also going to use repeatedly. So this finite set, since the sequence is non-zero, so this is a finite set of positive numbers, and it has a minimal element. So there exists some m prime, which is going to be the minimum of those, and it's going to be strictly bigger than 0, right? And now, if I choose m to be the minimum of this m prime, so this positive number, which is one of those, right? It's strictly non-zero, and b half that we've showed previously, then for all we will have that for this number m, what we have is that this is bound below to the entire sequence, right? Because for n that is greater than n1, the sequence is going to be bigger than that, and for those the sequence is bigger than that. So if we choose the minimum, this is bound from below for the entire sequence. Okay. So now if we consider this distance, then what we have then that 1 over bn minus b is bounded by this. The important part is that this is now a constant, a positive constant, times bn minus b. And now using the same trick again, since bn converges to b, then this can be made as small as we please. So since it converges to b, there exists n of epsilon, which depends on only on epsilon. So that for every n that is greater than n of epsilon, this would be smaller than m times the absolute value of b times epsilon, and therefore for every n that is greater than n of epsilon, we would have that this distance is smaller than this, and we have made bn minus b to be smaller than m times the absolute value of b times epsilon, which is smaller than epsilon. And by this we have proved that the sequence 1 over bn converges to b, provided that this sequence is non-zero. So again, what we used here, it's just a side effect of this proof, is that the sequence which is non-zero and converges to a non-zero limit will be separated from 0 by some positive number which is strictly bigger than 0 and will be bound below for the entire sequence as we've seen here. So let's see a Desmos visualization for this, for a particular sequence, of how it looks. Let us see an example of a sequence which is non-zero and converges to a non-zero limit, that it is indeed separated from 0 by some positive distance. So if we consider this sequence dn, it converges to some small number 0.1 plus this term 1 over n, and we have this term which gives it some oscillation, but all in all it's smaller than in its absolute values than 1 over n here, than even 1/2 of 1 over n for n that is greater than 2, then eventually this sequence is strictly positive, and it's going to be, well, it's going to oscillate, but eventually it's not going to approach 0. It's non-zero, and its limit is non-zero, so it can be bounded from below by some positive number. It's separated from 0. So let me show you what I mean. So if we plot the sequence, so at this scale, it seems that the sequence with this size of dots, that the sequence can maybe approach 0. That's at least how it looks. So let us now project the whole sequence on the y-axis, and let us zoom in. So indeed, even on this scale, when we zoom in, we see that the sequence is close to 0, but then we see a glimpse of hope. Then it is separated and can be bounded from below. This is what that's intuitively clear, but that's what we're proving. And if we were to draw this constant, for example, this line, y equals to 0.5, then this is a bound from below to the entire sequence. And basically what I'm saying here is that every sequence which is non-zero and every element is non-zero and converges to a non-zero limit, it can always be bounded from below. At least the sequence, the absolute values of the sequence can be bounded from below by some threshold that is bound below this number that is strictly positive and smaller than all the elements of the sequence. And therefore we can use it to bound it and to say, okay, the separation from 0 of the sequence is at least this number. And that's what we proved in that proof. It was like a side result. So we have proved essentially that the sequence 1 over bn converges to 1 over b. Okay, and now we're going to prove the final part, which for the quotient of the sequences. So now using part 3, which says that the product, if sequence one sequence converges to a limit and a second sequence converges to the limit, then the sequence which is their product converges to the product of the limits. So now we're going to use this third part of this theorem that we have already proved to prove the result for the quotient. Now we have the sequence an under the assumption of the theorem. It converges to the limit a. And now let us consider the sequence cn, which is 1 over bn. And we have proved that under the assumption that bn is non-zero and the limit b is non-zero, the sequence 1 over bn would converge to 1 over b. And therefore, we conclude that if we look at, we have this, then the sequence an over bn is identically equal to this product sequence an times cn. I mean, for every n, this is just exactly the same sequence by definition of the sequence cn. Now, the sequence an converges to a, and for cn we have proved that it converges to 1 over b. Therefore, by what we have already proved, an times cn would converge to a times 1 over b, which is a over b, but this is exactly the same as the sequence an over bn. Therefore, the sequence an over bn converges to the quotient of the limits.